Yulin as our speaker today. Joshua is a final year PhD student in physics at UIUC and has also spent time at the Flatiron Institute and Google Research. His research is focused on applications of machine learning to astrophysics, including dark matter, neutrinos, gravitational lensing, and black holes, as we'll hear about today. We're very excited to have him here. Joshua, please take it away.
Right, sure. Thanks for having me. I'm Joshua. So can you hear me just fine? My voice is usually pretty low, so like just at any point, let me know. So yeah, thanks for having me again. Pleasure to be here virtually. So today I'm going to talk about some of the project I've been working on, which I thought is pretty exciting, so I want to share it. The machine learning application for the Event Horizon Telescope. And this work has mainly been done with lots of collaborators at the University of Illinois, at Urbana-Champaign, and also within the Event Horizon Telescope collaborations. So since this is actually my first time here, so I thought I'll maybe introduce myself. Oops. Can you guys still see my screen? I think. Is it still working?
Yeah, it looks good now. Thanks.
All right, cool. Yeah. Yeah. So so thanks very much for the kind introduction. So as I said, I'm a final year PhD student, and this year I also spent time at Flatiron Institute and Google Research as an intern. And before that, I actually grew up in Taiwan, so I did all my master and bachelor in physics from Taiwan. And my research spanned wide range in like machine learning application in astrophysics. And I'm also a member of EHT starting last year. So I have lots of interest in astrophysics, but also on the machine learning side, I'm also pretty interested in computer vision and machine learning interpretability for scientific research, and also a little bit of reinforcement learning. So today I hope to cover a lot of things about like the really exciting things about machine learning research that people are trying to explore within the Event Horizon Telescope collaboration. So there are obviously many things, so I'm just going to highlight a few due to the time. And so I think first of all, I'm going to highlight some of my work, which is done by within University of Illinois on feature extraction and black hole spin. And also the second part, I'm going to talk about recently people start exploring using normalizing flow for black hole image reconstructions. And also at the end, later on, I hope to bring a new idea of using a neural network as an end-to-end data classification tools for VLBI, very long baseline radio interferometry data. And also like how looking into the future, whether we can use machine learning to help us build a better future telescope, and mention some of the future works and right there. So the story begins with the first image of a black hole. 2 years ago, the collaboration announced that we have a first image of a black hole. And to give, so I think some of people right here may not be that familiar with astrophysics behind it. So I thought about taking a few minutes just to broadly explain the idea behind it. So this is the first image of a black hole at the M87 star at the center of M87, which is 53 million light year away from us. So it's more than a 10 to the 9 solar mass black hole. So it's actually pretty huge. So the physical size, you can actually fit the whole solar system within it, and no problem. You're just pretty huge by scale. But because of the distance, it's actually pretty far away from us. So the actual angular size, it's super small. It's actually 40 microarcsecond. So 40 μAs. So like if you think of the resolution of this, it's to give you an analog, it's more like you're trying to resolve a golf ball in New York from Los Angeles or San Francisco, and you try to resolve all the tiny details on the golf ball. So in order to do that, you actually need a crazy amount of resolution. And before EHT exists, I think the best resolutions for this telescope is like still 1,000 times way shorter than the actual resolution needs to be. So then the topic becomes like, how do we do black hole observation then? So to do it properly, basically people need to pick a right wavelength, and because of several reasons that you don't want to have too much foreground absorption or noise or dust to interact with the light coming from the black hole from those synchrotron radiations. And in order to do that, you actually need to have a lot of radio telescope around the globe. And actually, people figure out that because of some optical constraint, if you want to resolve the black hole, you actually need to have the size of the telescope that is as big as the diameter of the Earth. So at the beginning, people thought, wow, that's absolutely crazy. How could you build a telescope that is so big? If you build that, then we will have no other space to live and do other stuff. But people also figure out that if you use radio telescope around the world and try to hook them up as a network, and when you do the observation, when you take all these radio telescope and pointing them toward particular sources you want, you can actually treat it as a sparsely distributed telescope, and later on use some computer algorithm to try to reconstruct these black hole image. So that's how the Event Horizon Telescope actually works. And the technique behind it is called radio interferometry. So the idea is that if you have some particular source on the sky, the light will come in as a propagated wave. And if you have two antennas at different location, the waveform will hit one of the antenna first and hit the other later because of the geometric distance. So there's going to be some phase difference between it. And so if you have many pairs of telescope, you can basically have many pairs of, you can have made these pairs of measurement into something we call visibilities, and later on use these visibility with some computer algorithm to reconstruct the black hole image. So due to the time, I won't jump into detail, but feel free to ask me some question later on. So the idea is that you actually need to collect some of these data, and because these data are like pretty huge, they're petabyte scale, so they need to be transported by airplanes or truck or something like that, and back into some of the data center, and you use some correlator and do further data reductions and use some image reconstruction method to reconstruct the black hole image as I described before. So that's basically how the Event Horizon Telescope work at the back end. So now coming back to the question is that we've been trying to think about like what can machine learning do to help us understand black hole image. So this is going to be the first project I'm going to mention today. So the first project is called Feature Extraction on Synthetic Black Hole Images. So the story begins like with, so as an astrophysicist, when we saw this black hole image, we was amazed by how beautiful this image is. But at the same time, we also want to understand what kind of physics can we learn from this black hole. For example, like, can we learn the spin of the black holes? And spin is very interesting because spin actually changes space-time geometries around the black hole and also inside the black hole, which we couldn't observe, of course. But and the other question we have is that, can we do it in a data-driven ways? So what I mean by data-driven way is that obviously we only have one real data at this moment. So obviously a lot of works needs to be done first by simulation. So that brought us to some of the simulated data our group at University of Illinois has been working on. So these are synthetic black hole image that represent, try to represent for M87 stars. And so on the left-hand side, these are full resolutions of our simulation. And on the right-hand side, these are the same image that have been confounded with Gaussian blur to represent what the current Event Horizon Telescope would observe. And these simulations are done using something we call GRMHD, the General Relativistic Magneto-Hydrodynamic Simulation, and GRRT to basically ray tracing all the 3D structure into a 2D image. So as I said, these are black hole image, but honestly, they are actually black hole. Black hole is actually evolving. So these are actually some of these are black hole videos, as you can see. So in order to create a really large like training set, we actually run lots of these simulation, and basically we can take a lot of snapshot from these images and basically create a pretty huge image library and try to use as a first attempt to understand how can we learn the spin of black hole from these synthetic data first. So as I said, the black hole is actually evolving. So and spin is actually parameterized by the parameter A, which is a range from physically could be range from a +1 to -1. And so as we can see, because the black hole is actually evolving, so what we notice when we look at these synthetic data is that we realize that the in-class variation is actually pretty huge, even across the same spin. And it's actually huger than the variation across different classes. So at that time, people thought that it could be quite difficult for you to just take one snapshot of the image and directly tell what the spin of these black hole is. And to make it even worse, I think one thing we did notice in the simulations is that sometimes the black holes which have different spin could look actually pretty similar to other black holes at a given moment. And for example, the one that I selected in the red box, they are actually contain different black hole spin, but they look very similar. And if you blur it with what the current resolution you'll see, it looks almost identical. So if people was trying to use some like chi-square fitting on top of it, and these wasn't working very well for some of the fitting method. So one of the things that we obviously turn our attention to is that could deep learning help? And as you can see, like so now once we have these question in mind, the problem could be rephrased as, given enough of these images and labels, can we try to estimate the parameter of our interest? And due to time, I'm going to mention spin for these cases. And so these are actually pretty standard computer vision tasks. So I won't jump into detail about the neural network architecture, but we choose a ResNet 18, which is a pretty classic. I personally really like ResNet 18 as a computer vision tools. So basically change the last layer so that it could output the parameter of our interest and do a mean square estimations on those parameters. And we train on like 100,000 of these images and validate on another 100,000 images and on GPUs. So after training those stuff, then we want to do some testing to make sure our neural network is working properly. So we actually build up 3 different levels of blind data set to test how general our neural network is. So so these are the histograms of the spin distributions of our data sets. So in blind data set A, we have the same setting, the same parameter setting as our training set, even though these images have never been shown to the neural network during the training phases. And if the neural network is working really well, then the idea is that you should see almost 5 delta function right here, because the spin should be falling into 5 of these categories. And to our surprise, that actually works pretty well. Then we thought, wow, this is actually working really well than our expected. Then we tried to see, we're worried about whether it's overfitting or just like doing some weird memorizations. Then we actually build up blind data set B and C to see how we'll generalize. So in blind data set B, we actually change the plasma physics of these black holes. So if never seen this plasma physics before. So as you can see, they start to have more scattering in some sense, but the overall performance is still pretty well from our perspective. And at the time, we thought, wow, this is also pretty exciting. Maybe it's really learning something. Then we give it blind data set C, which is in machine learning language, is kind of like an out of distribution data set. So we give them a spin like equals to 0.75 and 0.25, which is a spin value I've never seen before during the training phases. And one thing with notice right here is that when we plot out the distribution on blind data C, it's actually pretty heavily influenced by its prior. But when you take a mean value of these distribution of these blind data set, it's actually pretty close to the mean value is actually pretty close to the ground truth. So it is at this point that we thought, wow, maybe our neural network really learned something physical that that works really well, and we want to understand why. So as a physicist, like, or as a machine learning people, like, sometimes when we train model, like, we just basically dump a lot of data to a big nonlinear function neural network. And this is a cartoon I took from XACD that I really like. But as a physicist, that wasn't very satisfying. So we decided to take a look to learn what the, want to learn what the heck these neural network actually learns. So what we end up doing is that we decide to take a look into some of the intermediate output called the feature maps of these convolutional neural network. So one of these features about these convolution of the feature map is that they are actually the intermediate product of the convolutional kernel in the ConvNets, and usually there are some downsample effects of it. And because you can, usually in the ConvNets, you can have multiple convolutional kernels and have different layers. So there are usually multiple feature maps. And we decided to take a look into some of the feature maps of our trained ResNet and try to see whether we can learn something from those feature maps right there. So one thing when we plot out these feature maps from ResNet, and one thing we immediately realized is that at the last two layers, which is basic block 3 and 4, basic block is a structure in ResNet. Because of the downsample effect, usually the resolution is too low to us to recognize almost anything. And at the first convolutional layers, we can start seeing that the input image has been transformed into something slightly different, but it still looks pretty similar to its original input. But one thing we found really interesting is that the feature map of basic block 1 and 2, because we realized that we could actually still recognize the ring-like structure of this black hole. But on the other hand, we start to see a lot of interesting features showing up right here. And so one thing we decided to do is that to try to plot out all this feature map and try to compare it with the untrained ResNet's feature map. So what I say by untrained ResNet, these are actually pre-trained ResNet that have seen cats and dogs and ImageNet data sets, but have never seen a black hole and never been trained on how to estimate black hole span. And compare with the trained ResNet, which started from a pre-trained model and actually was working on the task to estimate span on these synthetic data. And by comparing these two, we actually noticed that some of the biggest difference is that there are lots of these spiral arm patterns start showing up right here. And at the moment, we thought that is really interesting. So we decided to poke around and plot out all the feature map to see whether they are really keen on these kind of features. And so on the left-hand side, it's all the feature map on basic block 1 of ResNet. And on the right-hand side is the feature map from a trained ResNet. And I select the one which contains, I personally think that they contains these spiral arm or low surface brightness features. And there's actually a lot of them showing up in these feature maps. So we thought that these are actually pretty interesting. And we thought about why they are interesting and why could they be related to span. So one of the reasons we think about that, so one of the reasons we call it low surface brightness is that when we plot our image in normal scale, it just looks like the left-hand side. But when we plot out in the log scale, we can actually see that there's lots of these low surface brightness features that are spiral arm patterns that are more far away from the photon ring or from the event horizons. And after chatting with some of the people in the collaboration, then we thought that maybe this has to do with something we call frame dragging. So in a curved black hole or a rotating black hole, the space-time geometry around the black hole do actually looks different than usually a Schwarzschild black hole. And previously, people didn't know that you can use this kind of feature to constrain spin. So most of the cases when people constrain spin in traditional way, they're focusing on the size of these bright rings right here, but they're not using a lot of these features on the outer edges. And what we found right here, I personally found it really exciting, is that there might be some information from the features that we didn't really fully explore using the traditional way before. So I'm pretty excited about this, and I think people are looking into this right now. Right. So just want to stop and see whether there are any quick questions.
Yeah, just a technical thing. So in this, so you seem to see more structure when you plot it in log scale.
Right.
Did you see a difference in performance when you were putting them in?
Yeah. So the answer is no. Like I think I trained them in both like normal scale and log scale, and the performance seems to be quite similar. Yeah, but that's a very good question, and this is actually going to bring up to what I'm going to mention in the next step, is that so first we want to understand, is there information in the full resolution image, and obviously that's not the real observation would observe, because we're going to have blurring effect and lots of noises. And so one thing we immediately do is that we blur the image and also add some Gaussian noise on the image domain to try to represent what the Event Horizon Telescope will observe. And so on the left-hand side is the full resolution version of our blind dataset performance. And on the right-hand side is the one that are trained it with blurred and noisy conditions. So as you can see, like the scatter becomes pretty huge, and which is almost no constraint on spin. And that's actually pretty encouraging for me, because I that's also what the collaboration, like, I mean, people are doing traditional analysis, like have the conclusion about MADISANE, is that given the current condition, it's really hard to constrain spin at this moment. But at the same time, we do also find that there's still some tiny peaks, like they're spreading around. So they do have some, neural network do have some sort of constraint, but it's very like loose at this stage to claim that neural network have any estimation on MAD7 at this moment. But we are pretty excited about this, because like I think in future, or in the last section of the talk, I will talk about some of the future telescope people are building on to try to see whether we can better resolve the black holes and estimate their spin. Right.
Sorry,
So
just a quick question. So this, the blurring that you've done here is different from the blurred images that you actually used for the training set?
So we blurred with a Gaussian kernel, and I think so we trained two different neural network on two different conditions. One is the full resolution, where there's no blurring on the left-hand side, and on the right-hand side is the blurring. And we also add noise, because that's how the real observation actually works. Right. So yeah.
I see. Okay, thank you.
So yeah, thanks for the question. So I think the next question, like people, I was working with Charles, who's my senior collaborator, and he asked me, like, can we directly apply our training neural network on real images? And my reply is hell. Yeah. So I raised up a few challenges when I thought about this. Can we really? So these are trained on simulation. Can we really apply it on the real images? And there are challenges from noise model and using simulations as a training sets, etc. But one of the problems that I would actually like to point out at this stage is that there's actually image reconstruction process involved when we talk about the first image of a black hole, which is what I'm going to talk about next. So as you heard from many scientific talks, you probably know that these are radio telescope data that are they are taken from radio telescope, and the real data actually lives in sparsely sampled field space, as plotted out in the middle, which I'll explain what's going on in the detail. But usually when people try to reconstruct the image from this measurement, usually the reconstruction will look similar to the input image, but they are not exactly the same. So if you want to try to apply on our neural network, train on image domain directly on it, it will be quite challenging because there could be some uncertainties right there. And so these are the visibility plot I took from the collaboration paper. So to me, this is actually the first real image of the black holes. And these might look a little bit complicated, but let me explain really quick. So on the left-hand side is what we call the UV sampling space. So imagine you have a black hole image and you have a bunch of telescope on the world, and you take the data, and the data actually lives in the Fourier space because of you're doing some interferometry things, kind of like doing some convolution something. I won't jump into detail right now. But the idea is that you're actually sparsely sample things in the Fourier domain. And because of the location constraint of these black hole, of these telescope, you're only going to sample some of the colored dots right here that looks like a caterpillar stuff. And these data are actually coming from pairs of telescope. So a pair of telescope could create one data point in Fourier domain. And then the reason why they have this caterpillar shape is that when you do the measurement on a black hole, the Earth is actually rotating at the same time. So in some sense, you're actually sampling different Fourier space when you do the measurement while the Earth is rotating. So which is actually a good thing because you can have more sampling of these Fourier space data. And so to give you an idea about, on the right-hand side, this is what we plot out the baseline and the visibility amplitudes. So visibility amplitude is like when you do Fourier transformation on a black hole image, you can actually have a Fourier version of these black hole image. And if you plot out their amplitude as a function of their radius, as a function of their baseline, you can actually think of it, you're doing some Fourier transformation on a ring-like structure. And if you do a ring-like structure Fourier transformation, you end up having like some of these spatial functions. So one key feature about this black hole image or this black hole data is that if your data are falling into this green spot, which you call the crescent model represent the ring-like structure, then that gives you an indication that you're probably seeing something like a ring-like things or a black hole. And if your data looks like a Gaussian blob, it'll look something like the black dot right here. So yeah, and so this is the real data of the MADISANE that I personally really likes a lot. And so actually the real data, the real visibility data, as described before, has been tried reconstruct into image by 4 different teams blindly when the image reconstruction process first happened. So this is a image I took from first paper of MADISANE. So these are 4 different teams use basically two different types of method. One is called regularized maximum likelihood. The other is called clean, which is what people traditionally use in radio interferometries. And I'm going to next cover something that I thought pretty exciting about normalizing flow, but I want to first explain what regularized maximum likelihood is. Right, so as you can see, the key reason why I thought that if you train things on simulate in image domain, then it's really risky to apply it to do anime estimation. And the real reason is that there are actually a lot of like uncertainties in this reconstructed image because of the sparse sampling and the noise. So we don't really know, without really understand some of these uncertainties, it's really hard to do some estimations. And so these are the 2 type of things that people have been working on. And I'm going to focus more on regularized maximum likelihood and how it can be hooked up to normalizing flow later in this talk. And so the good thing about regularized maximum likelihood is that it's actually a pretty Bayesian method. So you can pretty much track down the, you can set the prior, and given the data, you can calculate the posterior of this. But when you do clean, it's more like a traditional method, and it evolves with a lot of human experience, human expertise, and hyperparameter tunings. So it's actually pretty hard to evaluate the uncertainties using this method. So regularized maximum likelihood is basically like when you have a black hole image or black hole data collected from these telescopes, you have some measurement, which is what we call the visibilities. And because you have actually lots of these sparse sampling effect, so in principle, there are infinite possible of image you could actually build up. And then how do you pick like which image could really represent what we think the black hole is? So this is the idea about how people build up their regularized maximum likelihood method. And so it's pretty much a Bayesian way, like you have some observation Y, which is the visibilities, and you try to come up with some method that try to, given some prior, you try to maximize the likelihood of this function. So when you compare two different images, maybe because of the prior is different, or maybe because of the likelihood is different. So you end up having different values or different score for some of the images. And due to the time, I'm going to jump really quick, but the idea is that this is a Bayesian method given some of the data and try to calculate what's the best possible image for this black hole. And so this is the image reconstruction method that the EHT used. And I mean, two of the team used. And actually, I did a small play around with it. So I thought maybe it's pretty cool to show it around. I'm playing the video. Can you guys see it? Yeah, cool. So let me just skip to for a second. So I'm putting in some of the simulated images right here. And this is the EHT imaging pipeline built by Andrew Shell and other collaborators within collaboration. So it's basically like, as I said, a Bayesian method trying to find the best possible image given priors and given observables, and trying to basically gradually picking up the best possible image in right here. So as you can see that it's at the beginning, it looks pretty noisy, but at this as the process improves, like you can start seeing the ring-like structure, which starts to look similar to this black hole image. And this is actually one of the best open source software package I can find for astrophysics. So I have a lot of fun playing with it. So if you like radio interferometries, and yeah, I encourage you to play around with it. It's pretty cool. That's many stars on it as well. Yeah, so that's the idea about how the regularized maximum likelihood works. But the challenge is that how do you evaluate? So maybe you can basically pick up what's the best image. And the challenge is that how can you pick up the uncertainty quickly enough so that we can really know well, what the underlying distribution is. So this actually brought me to another group of work that have been done in Caltech, mainly by Hassan, who's a postdoc at Caltech, and Katie Bellman, who's now assistant professor at Caltech as well. And this work, I think, is at AAAI, and which they call deprobabilistic imaging. So they're basically trying to extend some of the image reconstruction method with normalizing flow right here. So now the question is, like, given some of the observable Y, which the collaboration really observed, you only have one, well, you have 4 days of measurement, but you have one such a measurement of MADISANE. What's the distribution of images? What's the uncertainty right there? And what kind of things can neural network do? So as I said, that the regularized maximum likelihood is a pretty Bayesian method. And so the idea is that you, in principle, can not only track down the maximum likelihood, but you can also track down some of the images that are possible, but not the most likely. And you can basically explore around it. And before neural network, people, I think, are pretty much rely on some of the MCMC method. But one of the challenges that the parameter space you need to explore is actually pretty huge. So it's actually could take some time. And so later on, I think those people figure out that you can actually use a normalizing flow to reconstruct the image. So I'm going to now switch gear to talk about how normalizing flow could help us reconstruct these images. So I checked the webpage and I saw like lots of previous talks seems to have covered normalizing flow. So I assume like most of you are quite familiar with what this is. So I won't jump into detail, but the idea is that normalizing flow is a neural network that can basically bring you from some kind of distribution and to other desired distribution of your interest that you want gradually. Um, and I think in this work they use real MVP, and due to time, I won't talk about detail about how real MVP works, but rather I would like to show how this could be hooked up to an image reconstruction algorithm that help you get the uncertainty of these black hole image. So as you're familiar with some of these normalizing flow generative models, basically you could start from noise, and usually you have a bunch of sample data sets in the image domain, like human faces or something. Then you can basically use normalizing flow as a generative model to generate these images. But what they are trying to do right here is that they use the normalizing flow, which is the input is construct in a 2D domain, and the output is image, but they don't actually have a set of possible black hole image setting up right here. Instead, they actually have the simulator, like the previously I mentioned EHT imaging right here. So you have normalizing flow that could generate some of the image, and you pass this image into your simulator and basically do some chi-square fitting on those to try to compare how close these images are to the real observables. And basically, by doing this, by hooking up a normalizing flow pipeline with the simulators at the end to the visibility and do some chi-square fitting, you could actually come up with a generative model using normalizing flow to basically try to generate black hole image just by fitting to the data. And as you change some of the noise distribution, some of the noise initialization, you can actually come up with different black hole image right here. And the next question is like, how do you properly evaluate the uncertainty right there? So what they actually do is that they are trying to optimize the network parameters with not only the likelihood, but also they include entropy loss, which they try to encourage the neural network to explore all the possible black hole image, even though some of them may not be the most likely, but they could like basically try to track down some of these possible image. And one thing they did track down right here is that, so they're basically trying to minimize well the KO divergence of their models with P of X, which is the image given your observable Ys. So I'm going to jump really quick into some of the sample they generated from this normalizing flow pipeline, which is that they put in some of the simulated data first, and this is the blur version of it because of the radio telescope we have. We wouldn't really resolve any detailed structure because we don't have a sampling for high frequencies. And they use traditional regularized maximum likelihood method with different initializations right here. And they also use their DPI, which is a normalizing flow based method, to try to generate black hole image from basically random noise and with one real observable data. So one thing, as you can see right here, is that the network seems to be doing pretty well on generating ring-like structure things, even though there's it only have one real data and only one simulations right there. And one thing I noticed that is that there are actually two different modes of these black hole rings. So for example, like usually in the ground truth, the brightest spot is on the top right, but in some sense, because of the sparse sampling of the data, some of the data that have the brightest spot on the bottom left could actually fit the data pretty well. So these are the real possibilities when you do the measurement with such a sparse telescope. This is something you could actually have. And these are some of the two different modes actually they figure out that they did a t-SNE distribution on those different modes of images, and they found that the real black hole image actually could be possibly distributed in two clusters. So one is the bright spot on top right, one is the one on bottom left, which is really cool, and using normalizing flow. And they also plot out their standard deviation, and their standard deviation divided by their mean value, because like usually some of the brightest spot will obviously have a huge uncertainty, but if you divide it by mean, you can actually see that they are pretty robust about the distribution at some place. Right. So I thought this is really cool, and they actually really apply this on the real data. And so in the real M87 observation, the collaboration did 4 days of observation of M87. And so they fit in the same DPI pipeline on the real visibility data. And these are the reconstructed black hole image along with their uncertainties. So I thought these are pretty cool and really helped us to understand the uncertainty of a black hole. Because, I mean, once we understand how uncertainty distributed right here, then we can have more constraint on the physical parameters and lots of experimental observations. Right. So yeah, this is a short summary about the DPI, which I thought is really cool. So right here, just want to stop and see whether there are any questions before I move on to the next section.
There's one question in the chat. I can read it if you can't see it, which goes back to earlier in the talk.
Mm-hmm.
How computationally demanding are the GRM HD model solutions? How much HPC resources did you require to fill in such a simulation database? This is going back to the early part when you were.
Right. So I don't know the exact number because I personally don't work on those GRM HD simulation, but it was pretty computational heavy. So that's one of the reasons why we only have 5 spring value in our training set, because like if you need to really create a new GRMHD simulation, then that's pretty computationally expensive, right?
I also had a question on this regularized maximum likelihood method. You mentioned, like, what sorts of things do you put into the prior?
Yeah, that's a very good question. So basically, different teams or different people can put in different priors, and what kind of priors you want to put in is actually based on your choice. But I think in this work, what they use is that they put in maximum entropy things as a prior, and also like there's a total variation square TV2 right here as a prior. So my understanding is that if you don't have observation, then if you have a really noisy image, and then entropy will be really high. So that's as a prior, that's more like unlikely as an image of any astrophysical object. But at the same time, they do want to pick a prior that doesn't really lean toward giving you a black hole shape, no matter what kind of things you throw in the idea. So yeah, I think this is a very good question, and I think it's still like people are still thinking about, always debating about what's the best prior to do for this observation. Yeah,
it's interesting, but they don't like explicitly put in any physics into the prior.
Right. I don't think there's any physics in the prior. So that's something we've been thinking about, is that if we believe some of the physical prior things, then can we put it in a prior and have better image reconstruction? Yeah, that's something people are thinking about. Yeah. Right. But I think at the same time, they do want to also make sure that they are not putting too much physics. Like they don't. One of the things about this black hole image is that they want to test with a black hole is right there or something like that. So putting GR right there might also be a really tight constraint in some cases. Yeah, cool.
There's one other question, if we have time, that just appeared in the chat.
Sure.
I can read it if it's helpful, or can you?
I couldn't see it right here.
Oh, I see. Okay, going back even farther, what sets the scale of the effective diameter of the telescope? Is there a simple back of the envelope calculation that would tell us that it must be order 10,000 kilometers?
Oh, I think there's some optical constraint when you given a wavelength and given a diameter, then how will like given a wavelength and given the object, like the angle of your interest and how big the diameter of your telescope needs to be. I think it's lambda equals to 1.22, something like that, divided by diameter. I think it's basically exactly that equation that we are figuring out how to pick the diameter of the telescope. So in fact, there are some people looking into shorter, different wavelength and try to see whether a different wavelength can have a better qualities of this black hole image. But they do also have other issues like some foreground issues that people need to worry about. So yeah. All right. Yep. So let me move on to the last stage of the talk, and I'll try to wrap it up quickly. So as you can see, like the previous section described a really good methods on trying to quantify the uncertainties of these black hole image. But on the other hand, we thought about tracking down the uncertainty is good, but is that always necessary? Do we really need a image reconstruction algorithm for us to do parameter estimations? The reason is that even though these are really good uncertainty estimation, but really depends on your prior and your fitting function, there's still like a lot of hyperparameter rooms for us to debating on which uncertainty is the real uncertainties right there. And so one of the things that we've been thinking about is that given observable, can we directly estimate some of the parameter of our interest, like spin of the black holes? And also in this case, I'll talk about another parameters. So before jumping in, I just want to mention that I thought radio interferometry looks really like autoencoder because basically you're trying to have an encoder that is physically spreading around the world and collecting some data. And your Latin representation is actually the visibility we have. And usually people hook it up with some decoder, which is the image reconstruction algorithm to create an image. But one thing I thought about is that if you can remove the decoder, but just connect it with multi-layer perceptron, for example, then the first part just looks exactly like a convolutional neural network, except like the really convolutional part is being taken care of by a real telescope. And you're coming from a real representation space and you're trying to get the parameter of your interest. So this leads up to the final project I'm going to mention really quick right here, which is classify the magnetic states around this black hole end to end in visibility domain without image reconstructions. So one of the things that we are also interested in is that we know that black holes, there are magnetic field around black hole, and they could be strong or weak, and they could be basically classified into different classes, which is called MADISANE, which is a pretty crazy name, but thought it was pretty cool. And the idea is that if you have some of these visibilities, can you do a parameter of estimation without reconstruct the image? And one thing we thought it's really possible because we already have these GRMHD simulation library. So one thing we tried to do right here is that we could also create a lot of these synthetic observations, synthetic visibilities, and basically use these synthetic visibilities as a training and validation sets to try to train the really simple neural network on different noise condition we tested right here, and try to classify whether do a binary classification of which magnetic states it is. So the thing we did is actually pretty simple, is that we put in the visibility, which I showed in the previous plot. And also there's another more technical things called closure amplitude and phases right here, which have to do with 3-point, 4-point functions of these visibilities, but I won't talk into detail about that. So basically you can imagine all your observable as a big vector, and you can pass it to a multi-layer perceptron and do a supervised learning. And that's one of the most simple things you can do. But on the other hand, I found it really profound because that you can actually have use neural network to do end-to-end data analysis or data classifications without image reconstruction, which is what most of the astronomers do these days with radio data. And it's usually a lot of work for them to clean the data and estimate things on the data. So one thing we did is that we tried to see whether we can estimate, classify these two different MADISANE states. And it turns out to be working fine at these the synthetic data. It's not perfect, but we have roughly 70% accuracies on given these on these um, synthetic data. And what we end up doing is that we create 4 different observational pipeline that fits exactly the same as the 4 days of real observations. So you might notice that some of them look more sparse. That it might be due to weather or some observational condition that the data quality wasn't that good on that day. So we could actually train a neural network based on our synthetic data directly on these synthetic visibilities and apply it on real data to classify whether it's a mad or sane states. So I thought this is really pretty cool. But I also want to mention that this is something that I'm thinking about whether it's a good thing or bad thing to do, because these are still trained on simulation. But just want to show that the neural network would give us potentially a tool to do end-to-end analysis in radio interferometry, which I thought was pretty exciting, right? Right, so I think due to the time, I'm going to skip the last section, but I think people are thinking about using machine learning to do a better design for future observations, and which you can imagine just optimization of your encoder, but each optimization might cost you a lot of money or budget. But I thought using machine learning for that is pretty cool. So I think with that, I'll stop at the summary and be happy to take questions.
Thank you very much, Joshua. Could have a round of applause. Yeah, that was a wonderful talk. Super interesting science. Any questions?
Yeah, maybe I can ask it. So in terms of prospects for future observations, so how do you have any intuition on how much better the image will get?
I think it really depends on. So I think there are people who are working on something we call the next generation Event Horizon Telescope. So they are going to have more sight on it, and having more sight is actually pretty good. At least from our understanding is that usually when you do these VOBI observation, the atmospheric noise could be different from these telescope side and that telescope side. So if you have some of the telescope, then that could basically give you more control about dealing with these noise, and you can have a more result or more steady image, I would say, if you're given the observables. And there are other people who are also thinking about doing something we call the space radio interferometry. So the idea is that the current Event Horizon Telescope is pretty much limited by the size of the Earth. So if you want to have a higher resolution, the only thing you need to do is to go to the space. So I think some of the people are thinking about maybe we can launch a few satellites, and you can do basically space radio interferometries. And I thought that's a brilliant idea. But there will also be multiple challenge if someone wants to do that. For example, like data transfer could be a real issue, because once you launch a satellite, you have a huge amount of data you want to transfer back. And yeah, that's all kind of new territories right there. But I mean, at least for machine learning, we could use it to show how much you can improve your encoder. Yeah, based on that. And you can have a better estimation on spin if you have more coverage at certain locations. Yeah.
There are no questions. I have two questions. One is I'm curious if there are other like big kind of analogous to this spin question, kind of big physics questions that people still would like to answer from these images, or what kinds of things are out there, since I'm not super familiar with black hole physics. And then the second question was, maybe you touched on this and I missed it, but do you use methods from like super resolution or things like that, just to, for instance, for your classification task, where you first just try to denoise the image to begin with before you use it for some other thing? Yeah, is that something I guess you've thought about?
Right. Yeah, these are two excellent questions, and I actually tried both. I think first of all is that yeah, there are many other interesting parameters that people are interested in. For example, like the mass of the black hole. We know that black hole have mass, but we really want to quantify their mass as an astrophysicist. So they do have a lot of things to do with how black hole actually evolve and grow. So mass estimation, it's quite important for us. And there are also some of the parameters or the angle. So we also want to figure out what the angles of the, so usually when black hole are spinning, there's a rotational axis, and we would like to know how like what's the angle between that axis towards the observer, just us. So that's also pretty interesting. And there are other people who are thinking about things beyond general relativity, but I'm not that familiar with that area, but I thought those are also pretty interesting. The second question is that have you tried using super resolution or denoising method? And that's something I've been thinking about for a long time, and I did some experiment. Yeah, I mean, given some of the synthetic data, we could absolutely do super resolutions, but I haven't really tried to make it work on the real data, so I couldn't tell. But at least on synthetic data, I think that's totally possible. It's basically you have more prior about like what the data should look like, then you can have a better resolution. And the other thing is about denoising. Is actually people are also thinking about using some machine learning method for clean to replace clean, which is some of the things that traditional astronomer use for reconstruct the black hole image. And I thought those are also pretty cool. I personally haven't played on that because I'm not expert in image reconstruction.
Cool, thank you. Any other questions, Sven?
Yeah, I have another question. So have you played around with adding the uncertainty information into the network? Because,
what do you mean by the uncertainty right here?
So in the sense like, okay, so on the simulated data, right, you have an uncertainty map as well.
Right.
Yeah, there, or respectively when you're talking about images, right, when you're
right
showing effectively these maps. So you could put in both, right, as an input.
Yeah, in principle, we could put in both. So I think there are two types of uncertainty we could put as an input right here. One is that we could put some of them as image domain inputs. So like you have a main image, you have uncertainty. No, I haven't tried that. But I would say that just these two might not be represented enough about the real underlying distribution, because like, as I said, there are two different modes. And if you take a main image and standard deviation, there still could be possible different combination of it. But the other thing I haven't tried, but I thought that I should really try, is that there are also uncertainties in the real observation from the visibilities. That's something I haven't tried. So I'm actually trying to combine it with something we call there's a multi-swag Bayesian neural network. So I'm trying to input the uncertainty and also output the uncertainty at the moment. But yeah, I'm still working on that.
Okay, if there are no other questions, maybe we'll end there. Thanks again, Joshua, for the talk. And yeah, we hope to see you all next time at the next session of Physics Meets ML in 2 weeks.